When a change in condition is applied to a system in equilibrium, the system moves so as to oppose the change. The stresses include change in concentration of either the reactants or the products, change to pressure in case of gases, and changes in temperature. Let us examine a hypothetical reversible reaction at equilibrium, where reactant A reacts with reactant B to form product C and D. If we add more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium therefore shifts to the right. If we added more C and D, the system becomes stressed and is no longer at equilibrium. So to counteract the stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What if we removed C and D as they are being produced, or if the concentration of C and D is decreased? The system is now stressed and is no longer at equilibrium. To counteract the stress, more C and D are produced so that the equilibrium shifts to the right. When the concentration increases on one side, equilibrium shifts to the opposite side of the reaction. When the concentration decreases on one side, equilibrium shifts to that side of the reaction. Next, changes in pressure. Now, this stress to a system at equilibrium is only applicable to gaseous systems. Consider a hypothetical reaction where 1 mole of A reacts with 2 moles of B to form product C and product D. An increase in pressure means there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause the equilibrium to shift to the right since there are few moles, 2 moles compared to 3 moles on the left. A decrease in pressure means there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles, so in our case, equilibrium will shift to the left. And so an increase in pressure favors the side with fewer moles. A decrease in pressure favors the side with more moles. If the number of moles is equal on both sides of the reaction, then changes in pressure will have no effect on the equilibrium. Next is change in temperature. Now, to consider what happens to a system at equilibrium when temperature is changed, we must first consider the energetics of the reaction in question. If the forward reaction is exothermic, then the reverse reaction must be endothermic. Let us examine a hypothetical reaction where reactant A reacts with reactant B to produce product C and D with the enthalpy change of -75 kilojoules. This means that when the forward reaction occurs, 75 kilojoules of energy is released, and 75 kilojoules of energy is absorbed when the reverse reaction occurs. So an increase in temperature will mean that the endothermic reaction will be favored to remove the excess heat and therefore counteracting the imposed stress. A decrease in temperature will cause the system to produce more energy. Therefore, the exothermic reaction will be favored. The conversion of nitrogen 4 oxide to dinitrogen tetraoxide is an exothermic reaction. Nitrogen 4 oxide is a brown gas, whereas dinitrogen tetraoxide is a colorless gas. What observations will be made if the temperature is decreased or when the temperature is increased? A decrease in temperature favors the exothermic reaction, so more dinitrogen tetroxide is produced. Since it's a colorless gas, the mixture appears pale yellow. An increase in temperature favors the endothermic reaction, so more nitrogen 4 oxide is produced. The mixture therefore appears darker brown. In conclusion, when the temperature of a system at equilibrium is increased, the endothermic reaction is favored. When the temperature is decreased, the exothermic reaction is favored. Addition of a catalyst does not affect the position of equilibrium, as it increases the rate of both forward and reverse reactions. So it only quickens the attainment of equilibrium. Let's go back to digging and refilling a hole. Imagine if you are both given bigger shovels. Although the amount of soil handled is larger with each stroke, the size of the hole remains constant. So adding a catalyst has no effect on equilibrium. Finally, industrial applications of chemical equilibrium, the Haber process. Now, the Haber process is the industrial process for the manufacture of ammonia from hydrogen and nitrogen. Note that this is a reversible process and that the forward reaction is exothermic. The Haber process uses the Chatellier'S principle to maximize ammonia production while keeping the operating and production costs in mind. Chatellier'S principle tells us that increasing pressure will favor the side with fewer moles, for our case, the production of ammonia. It will therefore make sense to conduct the reaction under high pressure. But we must also remember that it is expensive to build a plant that can withstand such high pressures. Thus, a compromise pressure of 200 atmospheres is used. What is the best temperature to maximize ammonia production? Since the forward reaction is exothermic, it would make sense to conduct the reaction at low temperature. The compromise temperature is 400 to 450 degrees Celsius, which is not exactly low but not too high. If a very low temperature was used, the rate of reaction will be very slow, even though the exothermic reaction will be favored. It will therefore take too long for equilibrium to be reached. So the compromise temperature of 400 to 450 degrees Celsius ensures that the reaction proceeds with sufficient yields. The yield in this process is 10 to 20%. But remember, unused gases are recycled, so there is no wastage. In addition, an ion catalyst is used. The presence of the catalyst does not affect the position of equilibrium, but increases the speed at which equilibrium is achieved.